And as director of the Simons Institute, it's my great pleasure to warmly welcome you all to our 11th annual Simons Institute Industry Day. So we've been doing this for a while. Some of you might have been here, know about us, but just a brief introduction to the Simons Institute. We are the leading international venue for collaborative research in theoretical computer science. We opened doors in 2012 with a generous grant from the Simons Foundation, which continues to support us generously. The Institute brings together the world's leading researchers in the theory of computing and related fields, as well as the next generation of outstanding young scholars. And the primary mode is to have thematic semesters on specific topics of current interest. And these span not only the foundations of computer science, because we are a theory institute at the core, but we have really put a lot of effort in enhancing the interface of theory of computing with various fields, obviously some very natural ones like math, but also increasingly physical sciences, economics, social computing, technology, quantum computing, and of course, these days, modern machine learning and AI. So we have a very broad view of theory and the impact it can have on the world. And if you think about computer science, what makes it really amazing is that we have these foundational questions on the one hand. On the other hand, we have an exciting, thriving industry which literally changes our world before we blink in a matter of few years, as we are very much witnessing these days, and particularly a lot of it housed right here in the Bay Area. And therefore, the industrial connections to us are extremely important to kind of have a sounding board for our thoughts and reveal new perspectives and directions for research. And on the flip side, I think a principled look at these computational issues can really guide the development of current and future technologies, especially these days as the technology really pervades all aspects of our life. I'll probably say more about this and our industrial partnership program in the afternoon session when we have our industry talks, and I'll say more about that. But just today's event really is, we'll begin with talks related to our programs. And we also have given by the program organizers, and then we also have talks, lightning talks by our research fellows. And as I said, we also have sessions where we have industry scientists give the talk. So it's going to be really an exciting day of talks, and I hope you all enjoy it. I know the weather has not been great, but given that you're already here, it's perfect day to be stuck indoors. So we have arranged great company for you to have great conversations, and hopefully it sparks new ideas and connections. And before I hand over to the program organizers, so the first session will be a preview into the programs we have had in the last year. So we'll start with the summer programs, talk about the programs ongoing currently, and then what's going to happen in the spring. So I'll hand it over to Sanjam, who will give the first talk. But before I do that, I want to give a big shout out to our staff who put together this event. It takes, as you can imagine, an enormous amount of effort to put together this event. I want to especially thank Amy Ambrose, who we have all interacted with for planning the schedule, and also Francis, Martha, and Lauren for really arranging all the specific things, the food and all the other things today. So big shout out to them, and thanks again to all of you for coming, and hope you have a great and productive day. Okay, with that, Sanjam on crypto.
Great. Thanks, Venkat. Yeah, so we had a summer program, Cryptography 10 years later, and the name had 10 years later because we had another crypto program 10 years ago. And so there are lots of developments that happened over these 10 years. And the theme of the program kind of rotated around proof systems, secure computation, and obfuscation. And since it's an industry-focused talk, I want to talk a little about how crypto has changed over the 10 years. And how the old days of crypto, where things took forever to transition to practice, or maybe 10 years was the minimum amount of time they would take for something to transition to practice. Now it's happening kind of very fast over months and years, where we publish a paper, someone in industry picks it up, starts implementing it. There are bugs likely, there are security holes, but with time, hopefully they will be resolved. And so this sort of cycle is happening very fast. So I wanted to give 3 examples where this sort of has happened quite a bit, and we're seeing lots of interest. So I'll start with proof systems, then move to secure computation, and then talk about one specific thing in the context of obfuscation, where we're seeing practical deployments already. And I'm going to start with proof systems, where it seems that they've taken over at least the blockchain part of the world. Okay, so what are ZK snark proofs? So you have a large computation, so some very expensive computation. It takes a lot of computational effort to compute it. So think of training an ML model. And you want to prove to a verifier that this computation was somehow done correctly. Okay, so it takes a day, potentially a year, to do this computation on this significant server farm, and a cell phone wants to verify this computation is done correctly. Obviously, one way to check that the computation was done correctly is to rerun it. But what ZK snarks do is they provide a mechanism to provide a short proof certificate, where this sort of short proof certificate is going to be a few kilobytes. And this verifier can verify that this entire computation that could have potentially taken a year with less than a second of time. Okay, so this is quite interesting. And the key challenge, so one additional feature that you can add is you can add the ZK property, which is zero knowledge, that even if this expensive computation involved certain secrets to do this computation, that information is not leaked to the verifier. So in the case of ML model training, so maybe your training data is not leaked. Maybe you're just leaking the model, but not the training data. And the key technical challenge that has gone, that researchers have been working on is how do we generate these proofs efficiently? Okay, so there's been significant effort both from academia and now industry, where there are multiple multi-billion-dollar startups, some which have matured more than being a startup, that are using this technology to enable scaling on blockchain. So you want to handle millions and millions of transactions on chain, and that's expensive. And the trick is, rather than having everything being verified on chain, you verify everything off chain, you generate a proof, and just the proof is verified on chain. Typically, when people talk about ZK snarks in industry, they don't care as much about the ZK property. It's just about cheap verification. But ZK property also has applications if you want privacy on chain. You want to be able to say that you want to buy ice cream using whatever cryptocurrency tokens or stable coins that you might have, and not leak information about who's making the payment. So this is the first application which I want to talk about, where we've already seen kind of the takeover. Crypto is really having a huge impact. The next setting is, which I said, secure computation. It can make sense both in the two-party and multi-party setting. In this picture, I have multiple parties. So you have 6 parties here. They have their private inputs. So, n parties here, they have their private inputs, x1, x2, x3, xn, respectively. These parties want to compute a public function. So they want to compute this function f on their private inputs, x1 to xn. So they want to keep their private inputs confidential. And some of these parties could potentially be corrupted. Okay? So they could be malicious, they could be colluding with each other, they could behave arbitrarily during the protocol execution. And we want the parties to learn nothing more than the output of the computation. Okay? So they already know the malicious parties do know their input. They could use their inputs and the output to get other stuff, but they shouldn't learn anything more than that. Okay, so this is the problem multi-party computation. A classical example is, from 80s is, with like n millionaires. Maybe today it makes sense to talk about billionaires. So you have n billionaires, and they want to figure out who has the most amount of money without leaking their individual networks. So that you could use secure multi-party computation. Another example is you could use this to play poker online. Okay, so you could have a secure card shuffling without having to trust someone who shuffles the cards. Again, MPC is having a significant impact. I'll talk about one multi-billion-dollar kind of an industry that has spun out, specifically for MPC signature wallets. So typically in cryptocurrencies, or more broadly, we're not seeing the effect as much yet, but hopefully soon. in certificate signing and things like that. So you have a secret key SK. You don't want to store it on your cell phone, right? So this secret key locks a lot of money. You don't want to store the secret key on your cell phone. And the idea is you want to split it across multiple players. So you have n players here. You want to take the secret key and secret share it, or what we call. So every party has a share of the key. No individual person has access to the whole key. But so in the simplest of cases, all of them need to come together to reconstruct this key. But we don't want them to come together and reconstruct the key. Instead, when a message comes around, so I go to a shop, I want to buy ice cream, I want to pay $4 or whatever the ice cream is worth. These parties that hold shares, they could be located in different jurisdictions. One is in the US, another is in Switzerland, and so on. They run an MPC protocol, which yields a signature sigma saying that I transfer $4 to the ice cream shop vendor. And so now, never is the secret key held in one location, but I'm able to do this transfer of money securely. And if let's say in some jurisdiction the government wants to get hold of one of the keys, it will not be able to sort of get hold of the assets that I have. Okay. So correctness here is if all the parties come together, they can generate the signature. And unforgeability requirements is even if you have secret keys from subsets of the parties, you will not be able to generate signatures on messages you had not previously seen. So sort of the simplest case. In more sophisticated cases, you can talk about robustness, where you don't need all n of them, maybe you need t of them, and so on. So this is something that already, as I said, the multiple companies that are serving this to customers who hold significant amount of assets. I think basically by regulations, every bank is required to use this kind of a system, not hold secret keys in one place. So this is really being useful, widely used in the blockchain ecosystem. Another example, which is not blockchain specific but has significant applications, is private set intersection. I'm going to talk about in the context of spam detection, but it has other cases. So here's a user. If you have I believe this is already deployed by Apple. So if you're a user who has an iPhone and you get a call, you want to check is this spam before you pick up the phone. And so to do that, you want to check in Apple's database, is this a spam call or not? And Apple doesn't want to share the list of spammers with everyone. So you run a two-message protocol where by the end of the protocol, you don't share who called you to Apple. Apple doesn't share the list of people who are on the spam list, and you learn whether this caller is on the spam list or not. Okay? So if this is sort of, again, in the context of MPC. If the final thing that I want to talk about is in the context of witness encryption, which is a special case of obfuscation, and this is already hitting production. So in this case, we have a statement X. Think of any SAT formula. We have an encryptor who wants to encrypt this message M and generate the ciphertext. He generates the ciphertext. He doesn't know whether this SAT formula is satisfiable or not. He goes away. Okay, and so does the message with him. Maybe 100 years later, someone comes around and has figured out a witness for this SAT formula. So they have a solution, a satisfying assignment, and they want to use the satisfying assignment itself to decrypt the ciphertext and get the message back. The security requirement, maybe I'll skip it, but it's sort of roughly that if you don't have the witness, you can't decrypt the ciphertext. So this is making already into practice. A particular blockchain company named Aptos just put it in production 2 weeks back. So the example here is we have a user. He wants to put this transaction on chain. A key problem is before this transaction ends up on chain, it actually sits around in what's called a memory pool. So this memory pool is sort of visible to a lot of people. So for example, if you want to buy Apple stock, what ends up happening is as the transaction's waiting in the memory pool, someone comes, buys Apple at a cheaper price, and sells the Apple stock that they just bought to you at a higher price. And so the user misses out on a little bit of the profits. So in particular, before the transaction actually ends up on chain or is finalized, the fact that other people have access to it leaks information about the transaction and makes you vulnerable to market manipulation. So the solution that we built for this is, what if you put this transaction encrypted? So you don't send this transaction in the memory pool unencrypted, but this transaction goes encrypted. It ends up on chain encrypted. And the cool thing is, the witness to decrypt this transaction is the authentication information that it ended up on chain. So if it ever ends up on chain, it gets decrypted. If it doesn't end up on chain, it doesn't get decrypted. So that's sort of really powerful that, whatever authentication mechanism is allows for the decryption of this transaction. Okay, so this is, as I said, deployed by Aptus a couple of weeks back. And I know of other cases where this is deployed. And if this is to make it to NASDAQ or something, where we do want this sort of attacks not to happen, then we're going to see these technologies more and more. Okay, thank you.
Thanks a lot, Sanjam. That was really inspiring connections between theory and practice to start off the day. In the interest of time, there's a quick question. We can take it as the next speaker sets up. Otherwise, catch the speakers during the break. So next we have Umesh Vazirani. There was a very exciting quantum summer cluster alongside the crypto program during the summer. And Umesh will tell us about highlights from that.
I'm setting up, but I have to say that I was tempted to yield my time to Sanjam to tell us more about what he was already saying. Okay, so let me say a little bit about our summer cluster on quantum computing. This was, as many of you know, part of our quantum research pod, which has many other activities here at the Simons Institute. How do I?
Say hello.
Okay. Okay, so let me, there's a lot to say about this summer cluster. We had, a large number of senior visitors, like 20 maybe, but the main thing about it, the unusual thing about it was the number of students who came to attend the workshop and this cluster. And there was also a wide range of students from extremely advanced students to those who were trying to get into the field. Now, the workshops formed the backbone of this program, and I'll describe some of these workshops. So there were these one-day workshops, which is something that we had been playing with in the last year or two. They turn out to be a very effective forum for convening experts in the field to collaborate on either the latest issues, some important issue, or an open question, or a new technique, and seeing how we can leverage that. Okay, so I'll just touch on a few high points. So, what does this do? No, okay. Oops.
There you go, that's it.
Okay, so, okay, well, I'll just point. Okay, so one of these workshops on this was on this technique called compressed oracles. This was something that already the previous year in 2024 program in the spring resulted in, there was a one-day workshop which resulted in this breakthrough result on pseudo-random unitaries. So these are unitaries or, sort of quantum programs which look like they are completely random, but, like random unitaries, but you cannot tell the difference, even though they are implemented efficiently. So this was a very new technique, and the one-day workshop sort of explored it and led to this collaboration on a long-standing open problem, which was to show that QMA and QCMA are different. So what are QMA and QCMA? So these are the quantum analogs of NP. So where you have a short witness that convinces you that the answer to a certain problem is yes. So the question here is, should that short witness be quantum? That's in QMA. Is it a sort of polynomial size quantum state as a witness? Or should it be a classical witness in the form of a classical circuit that generates that quantum state? And could it be that these two notions are the same? And the answer here says, finally, that these two notions are different from each other, which is something we suspected for a very long time, 20, 25 years, but haven't been able to prove so until this point. There was a second one-day workshop on Gibbs sampling, which is an approach towards, in quantum algorithms in terms of quantum simulation or creating interesting quantum states. There's been a lot of work on that recently. Quite a lot of it, the foundations have been laid by Anthony Chen, who is a postdoc and who's here at the Simons Institute in the quantum pod. And the major issue there was, do these algorithms converge quickly? We know that we can implement each step efficiently, and if they converge, then they produce Gibbs states, which is what we are trying to do, these low temperature states. But do they ever converge quickly? And so this was sort of, this first paper, which was prompted by, was inspired by this workshop, actually gives the first major success in this area by showing that if you have a 1D chain of spins, then this algorithm, the Gibbs sampling algorithm, converges quickly at every temperature, no matter how low the temperature is. But then, for many chains, these dynamics don't converge quickly. And so then the question is, what do you do? How do you do quantum simulation? And the answer is that actually maybe we should instead of trying to create Gibbs states, we should be satisfied with metastable states, because they have many of the same properties. So that's what was the result of this second paper. Okay, now I want to highlight something about these one-day workshops, which is that they are a fantastic forum for collaboration between industry and academia. It's a relatively small investment in time to get a lot out of it, and also for actually industry collaboration. So let me just give you examples of this from some of these workshops. So there was a one-day workshop on decoded quantum interferometry, which is one of the, again, a very interesting new technique for designing quantum algorithms. And there were presentations by Stephen Jordan and Noah Schutte from Google on some open questions in this area. And Sayun Raghavan, who's a grad student at MIT, was in Noah Schutte's talk. And he realized that the open question that Noah was speaking about could be attacked by a technique that he had been thinking of. And that immediately, or well over the next month or two, led to this paper on designing DQI, leveraging these unambiguous state discrimination algorithms. Now, in the following workshop, there was a presentation by Andrew Georgiou from IBM about his work on verifiable quantum advantage. So one of the big questions in quantum algorithms is, can you design these, an experiment similar to the Google quantum supremacy experiment, okay, which we could run in the near term, meaning 100, 200, 300 qubits, but small number of total operations so that it could be done on a near-term quantum computer in this next year or two. And in such a way that it cannot be classically spoofed, and moreover, we can classically efficiently verify that the quantum computer managed to solve the problem. So which part of it did Google not actually do? Well, of course, can it be classically spoofed or not? This is always an interesting question. But the part about verifying that the quantum computer actually solved the problem, this is where, until now, we don't have a practical scheme where you can verify in less than exponential time. So Google had to spend exponential classical effort to verify that their quantum computer. Okay, so Andrew, we've been thinking about this for many years. We have many schemes, but none of them quite get to this point of being implementable in 100, 200 qubits. So this was a scheme that Georgiou presented that that seemed to work, and it was a beautiful scheme. It also was an act of great courage from his manager, who allowed him to come and speak about it, because they were really thinking they had this scheme that they could implement in 100 or 200 qubits. It had all the right properties. And they were, so speaking about it publicly like this took a bit of guts. It was a good thing that they did. It was not only courageous, but also wise, because by the end of the workshop, Noah realized that you can break the scheme using the Aurora-G algorithm. Okay, so this was, of course, a big setback in some sense, but in terms of science, it was a step forward. If we went ahead a couple of months, we had our Quantum Industry Day in October, and by then, Andrew and his co-authors had managed to it looked like the scheme was completely broken, but they managed to fix it using now very interesting techniques. So now they were still using correlation, bend functions, obfuscation, but now using the hardness was based on a group membership problem. Again, an act of courage to come and speak about it. Noah was not in the audience this time, so it was a little bit easier. But the jury is still out. We are still going back and forth about whether it works or not, whether we can break it. So it's really, in some sense, this was a real example of how the Simons Institute provides the neutral ground where, there's no hype and you can actually talk across industry, academia, or industry. My final example is another talk from Quantum Industry Day, which William Kretschmer, who was a postdoc here in the Quantum Pod, who works on really theoretical, at the theoretical end of quantum complexity theory. So he spent the last 2 years here working with Quantinuum on taking a scheme for, unconditional separation between quantum and classical, now not in a computational sense, but in an information sense, in terms of the total amount of storage required. And he spent a couple of years sort of delving into the resource requirements and the nitty-gritty of actually porting this scheme onto Quantinuum's processors. And so they finally did the experiment earlier this year, and there was a paper in Nature about it. So that was this talk. So, okay, so those are examples of the kind of setting that Simons provides for this kind of collaboration. Okay.
Thank you very much.
Thanks a lot, Umesh. Very inspiring. I guess any quick question as the next speaker. Okay, so good. All right, so now we'll move to the current ongoing programs. We have actually 2 programs in parallel, which is our typical mode most semesters. We have one program on complexity and linear algebra, and the other program on algorithmic foundations of emerging hardware technologies, computing technologies. And we'll hear from the organizers of both these programs, as well as sort of a talk which unifies the perspective from both. So that's on that next. Yeah, first we have J.M. Landsberg on complexity and linear algebra.
Okay, so we're in the middle of a wonderful semester, and I'd like to tell you a little bit about what we're doing. But before that, let me tell you what may have been the most important impetus for this semester. Well, it was in 1968, but before that, I just want to point out that people have been trying to solve systems and succeeding in solving systems of linear equations since ancient Mesopotamia even. And by the time you get to ancient China, they were actually studying them in a way that's not so different from how we study them today. And in fact, the ancient Chinese knew about something that we call Gaussian elimination, which is a very efficient way to solve systems of linear equations. And what happened in 1968 was kind of funny. Strawson, a probabilist, well, he said, okay, so Gaussian elimination is done by multiplying matrices, and we've been multiplying matrices for a long time. He said, let's prove that the way we multiply matrices, row, column, is best possible. And he failed. He actually showed that you can do better. And now, probably in 1968, this was like extremely exciting from a theoretical point of view, but maybe not so important for people's daily lives. But now, every day, AI uses roughly 1% to 2% of the world's energy that's generated multiplying matrices. Multiplying unstructured matrices, basically, is what it comes down to. And any improvement of this could result in dramatic savings for the planet. So then we have a lot of questions you ask. So I'm more on the theoretical side. I want to know how much better can we do? Or maybe we can't do much better at all. But there's a whole group, an active part that I've been learning about in our semester, of people who are actually improving not just on a grand scale, but on a human scale of matrices of reasonable size, just improving things. Even the slightest improvement would make a huge difference for practical things. So let me go quickly through what we're doing. Like I said, we're interested in doing better both in theory and in practice, or maybe proving that we can't. But I want to go to another theme, the last one, about numerical linear algebra on a large scale, and a possible novelty about our program with respect to that. So let's just think about a single matrix vector operation, but it's a very big matrix. And maybe it's sparse or has some special properties. We want to exploit that as much as possible. And there is an extraordinary amount of literature on that. But what there is not as much are solid theoretical foundations. And here, in this semester, people are working quite hard to lay theoretical foundations. And even if you don't care beans about theory, what's been happening is a feedback loop that the theory that's sort of trying to underlie these algorithms that people have been using on an ad hoc basis gives us new insight to develop new algorithms and make new, actual practically efficient things that we can do better. So that I think is maybe going to be a high impact part of this program. And not only that, there's a large list of open problems that are being accumulated in this sort of, I can't say emerging area because it's been around for a long time, but this bringing together of the theory and the practice, I think, is a very strong component of our program. Any questions, by the way? Okay, so let me tell you some exciting things that are going on. For me, so if you go fishing, especially fishing in a stream, where's the best place to go fishing? No, you're out of stream, but you want to go where two streams come together, right? That's where you're going to get the most fish, and it's not a joke. Obviously, you've never been fishing, but anyway, what we've been developing are new connections between areas that maybe previously seemed unrelated. I've already mentioned this numerical linear algebra in computer science, which I think is going to be very high impact. Let me tell you something much closer to my heart. I am in training a geometer, and it's only recently in my life that I've gotten interested in computer science. And in computer science, studying, for example, complexity of matrix multiplication, probability has been used extensively. Strawson was a probabilist. He's had a dramatic impact on the field. But if you want to prove something like lower bounds, prove you can't do much better, you're sort of forced to use geometric techniques. And these two things are living in different worlds. And it is one of something we're trying to accomplish this semester is bring these two different mathematical worlds together to study these questions in computer science. Another thing which strikes me as very strange, there's a piece of mathematics, you don't need to know what it is precisely, but people have been studying this area called geometric invariant theory and orbit closure problems for at least 75, 80 years. And up until 5 or 10 years ago, this was viewed as pure mathematics as you can get to. But then there was a series of papers starting with, I don't want to say Gervitz was the first, but there was a bunch of papers that, especially Wigderson and his group, that started realizing that, one, there's these quite practical questions that could be viewed as orbit closure problems, and on the other hand, that this orbit closure thing, which was viewed as something purely theoretical, could be treated numerically, and actual practical algorithms, both developed for the questions of practical interest, but also maybe some of these problems of theoretical interest. And similarly, in numerical linear algebra, there's been a whole bunch of use of randomness and applications of randomness, which feeds into the theory. I don't want to overstay my welcome. Let me just go the other direction. We had a workshop on matrix multiplication. And one of the exciting things was getting a bunch of very different people in the same room talking with each other. So there's been a lot of excitement about AI, Google DeepMind, being used to develop new matrix multiplication algorithms, but there's competition. SAT solvers, random walks on graphs, which goes under the name of flip graphs, and more classical methods such as gradient descent. And we got all together, and it's not clear which of these things, well, I shouldn't say it's not clear which of these things is going to win, because that's not what's going to happen. There's been a lot of back and forth of borrowing of ideas from these different groups that fed off of each other, and it's been quite exciting, and I've been really enjoying this semester. Thank you for your attention.
Questions? So you mentioned Google DeepMind. Can you specify which algorithm you mean when you say AI, Google DeepMind?
They called it alpha solvers, alpha evolve. I forget the
that one.
precise name, but yeah, I know how it, well, I remember the description of how it works. You just feed it any old code to solve a problem, and then it keeps modifying the code to make it better. And in this case, it was a search algorithm. You're searching for some new matrix multiplication thing. They put in something really stupid, and then it got better. And this is how the others, the sort of competitors, interacted with them, because then they said, well, let's feed it a good algorithm, these ones that have led to some really good things. And then it's got a head start. And actually that was kind of quite a lively topic of discussion during our workshop.
Thank you.
Thank you.
All right, we can take other questions during the breaks. Yeah, the other program happening is Algorithmic Foundations for Emerging Computing Technologies. Kirk, Pruhs is one of the organizers and will tell us about it.
So at least the initial impetus for this program came out of Simon, so I'm going to sort of start with the backstory that probably led to this. So this is a influential article in CACM by Hennessy and Patterson. It was associated with their Turing Award, which predicted a new golden age for computer architecture. So, what was the basis for this prediction? Well, a lot of the laws, that we've been relying on, Denning scaling, Moore's law, are sort of coming to an end. So for decades, people just kept doing the same thing, just better. That had to come to an end. So now if you want to do better, you can't just rely on Moore's law. You needed to do something else. So, this is the key quote from their article, that they predicted a Cambrian explosion of novel computer architectures, which means exciting times for researchers in this area. And so if you're not any more familiar with Cambrian than you are with fishing, during the Cambrian age, there was a vast increase in the number of species for reasons that probably somebody knows, but I don't. During the boot camp, one of the talks was by Mark Horowitz, and part of the talk was just discussing, what problems these new technologies have faced with adoption, and the big one is just economic. Like, the cost of people of adopting a new technology is going to be large. Not much we can do about this, but the other issue was these new technologies are going to need management policies to manage them to compete with the old technologies where, the management technologies have been developed over decades. So, that's maybe something the algorithmic community can help with. Okay? So, I suspect that's the backstory of sort of how we came to do this. So, we wrote a proposal to, look at sort of an algorithmic take on newish computing technologies. So there were sort of two programmed goals. One was, kind of the direct one, like, studies these newish technologies, can we say something about managing them? And the second was sort of a longer term, broader term goal of, developing an understanding of skill of what interdisciplinary research looks like for algorithmic people with systems researchers. So I'm going to talk about the first one first. I'm just going to give you a couple examples of what's the sort of questions one might look at. So, given the recent importance of generative AI requires a lot of data. So the computing technologies that are doing this, a lot of them use high bandwidth memory, which is the newish memory technology. And so, what is high bandwidth memory? High bandwidth memory lets you get more bits per unit time to your processor. They don't get there faster. They just get more bits per unit time. Okay? So if you look up, books on operating systems architecture, algorithms, you'll see this problem of managing a memory hierarchy. Okay, we have different types of memory. The good memory, which is fast memory, is closer to the processor. The slow memory is farther away, and then you sort of have to manage this. Okay, so one could imagine a setting now where, again, over here with high bandwidth memory, this is the better memory. It's closer to the processor, but what's better about it is not that it's faster, it just has more bandwidth, right? So now you want to manage that, and now if you look at if you look at any of these textbooks, you'll find that, hey, LRU is a good algorithm for cache replacement on your good memory. Okay? With HBM, that's not the right policy. Okay? It's a bad policy. Okay? So you need some other cache replacement policy for HBM. All right? Here's one other example. This is kind of old, but it sort of it's good for the illustrative purposes. So these are a bunch of memory technologies. There's a bunch of characteristics. What I really care about is the vertical y-axis, which is the read time. So lower is better, it means you're faster, okay? And kind of down here toward the bottom is domain wall memory. So, it's kind of fast, so it's as good. And It's to the left, it takes up a small amount of volume, so that's also good. So just from this picture, that sort of looks good. But the one thing to note is like the read time here is not a point. For these other, the read time's a point, this is an interval, all right? Why is that an interval? It's because if you look at like where the bits are stored, it's like a wire. Or conceptually, it's a logical tape, like a cassette tape, an 8-track tape, wherever you are technology-wise, it's like a tape. So if the bit you want to read, if you're far away from the read head, it might take longer. If the bit's near the read head, where the read head is, it might be faster. All right? So you can imagine a research question is how, can I organize my data on the domain wall memory so that like I'm sort of down here toward the bottom more than toward the top, okay? Because I've smartly organized my data. All right, so now I want to just talk a little bit about the sort of the broader aspects of understanding appreciation in this area. So I asked, we just had notifications for acceptances for our big yearly algorithms conference. And I asked a bunch of postdocs, our postdocs are fellows who had papers, give me the elevator pitch for your paper that got in. Right, everybody, this is a skill you should have in academy. What's your elevator pitch in case you get in the elevator with the dean? And their elevator pitch was, in this conference 2 years ago, somebody got a 5 approximation. And I got a 4 now. That was their elevator pitch. So there's this like Guinness Book of World Records sort of view of research. There's these records for the various problems. And what do you do as research? You beat one of these records. And you should beat it for an important problem, right, if you want a good job. And also, if you ask the students, like, what do you want? They want a good job, and they want to get tenure, right? And this is how they view that they're going to do it, right? And how do they decide what the important problems are? Well, if the top conference accepted a paper 2 years ago that's 5, then 4 should be, 4 is good, right? That's better, right? That's sort of how it goes. And I'm one of the things I find sort of surprising about our research area is that even a lot of senior researchers have this view of research. Like I'm beating the records in my area. Okay? So one of the things we did in the boot camp is we had people come in, algorithms researchers, and talk about the research what it looked like with systems researchers. And there's a lot of really good talks, but let me particularly point out Martin Ferricksholden, which gave the best talk I have ever heard on doing algorithmic theoretical research with systems researchers. And part of it, this was the timeline for one of his results. He just decided he was going to sit down with some systems researchers at Rutgers, and they were going to find a problem. And they sat there for a year before they found the problem, because the systems guys would go, "This is a problem." And Martin would say, well, that's not really an algorithmic problem that we can do something about, right? There's not every problem is solvable by a smart algorithmic idea, right? So they they finally found a problem, so Martin said, oh, that's something we can do with. That's something we can do something about. They got the algorithmic result in 1 week. After a year of looking, then they spent a year implementing and testing, right? And eventually what came out of here is a bunch of best paper awards and systems conferences. Right? But this is a very different style and timeline of research. Like the world record view is, I look up in the last conference, in 5 minutes I have my problem, and then I spent 1 year solving it. It's just a very different style of research. All right. So, good. And so, the focus of the workshop has been more on finding problems. So after we had a memory management workshop, we had people formulate like initial research questions that came out of there. We had small groups, and then, you started with some initial formalization, and then it wasn't quite right, it was too hard, and the problem and the model changed over time. So we just went through this process. So the hope is, this is kind of an older researcher's game. Like, you don't expect postdocs to be doing this style of research. This is sort of full tenured professors do this style. But our postdocs hopefully get this so that when they get to be full professors, they can do this. All right, that's it.
Kirk, very interesting. Any quick questions as the next speaker sets up? I want to point out that this sort of long-range interactions between people from differing perspectives, that's actually one of the things where this institute and the structure really shines, because you really kind of have the opportunity to talk to people from a different field over months, often a semester, and you really get inspired and find new problems and so on. So I think this was very excited that Kirk focused on that aspect in his talk as well. Yeah, in spring we are going to have a program on federated and collaborative learning, and Nati is one of the organizers and will give us a preview of what's on tap.
Okay, so sorry.
Thanks to all speakers for keeping on time. It looks like we have a packed schedule, but we are off to a good start.
Okay, excellent. Okay, so hello. So I don't have the advantage of of speaking about something that already happened. So I'm not going to tell you what came out of the program. Hopefully, a lot will come out. But this program will happen in the, as Venkat said, starting in January. And so I want to more advertise the program and tell you a bit like why I think it's exciting. So first of all, I should say the program organized by these 6 organizers, but really the main 2 organizers are Ginger Smith and Peter Kairos. What is going on here? Okay. Ginger Smith and Peter Kairos. And already by the organizers, you can see that this is a very tight, the entire program, I think, represents a tight interaction between academia and industry. And Peter is from the team that essentially invented federated learning in Google, and Kunal, also one of the organizers. So what is federated learning? So the basic, or the original idea for federated learning is to train based on data on devices without ever sending the data to the server. So we have all these devices in our pockets, and there's lots of data collected on them, like everything I type, everything I say, everything all my emails, and that data is extremely useful for training a model. And the traditional approach for training is just send all this model to the cloud and do the training on the cloud. And the idea in federated learning is to keep the data on the device, and instead of actually sending the data to the device, coordinate the learning with the server. There's still a centralized learning framework. There is a centralized server, but the server interacts with individual devices and exchanges messages with them, but without actually ever sending the training data itself to the server. Okay? And the motivations here are twofold. So one motivation is to make maybe better use of resources, and mostly to reduce communication, because the computing resources here are kind of useless in terms of training models. That's not kind of the point. Reducing communication maybe is, so that's maybe less relevant for my text messages, but for example, when we want to train on like all the audio or video, so if cars have like a dozen cameras on them, they take a lot of video. We don't want to actually send constantly all the video from all 12 cameras on the car to the server, but we might want to use that for learning again without sending it. But really the main motivation was mostly privacy, like keeping the data on the device, both to ensure formal privacy guarantees, and also beyond the formal privacy guarantees, also to not have to deal with the data kind of being on the server and various implications of that. So this brings about a host of challenges, many of them with very strong kind of theoretical components. One is coordinating the optimization, and there are challenges here even in terms of distributed optimization, kind of very different regimes. You have lots of devices, but these devices are very high latency. They're very unreliable. This training only happens from some of these when the device is idle. I pick it up, suddenly the node disappears. There are also privacy, how to ensure privacy into this. So much of the work is focused on privacy. And then there's lots of challenges related to heterogeneity, both the data heterogeneity. The data that Venkat has on his device is fundamentally different from the data I have on my device. And we talk about different things. We use slightly different, maybe forms of English. but also more than that, device heterogeneity. So each of your computing nodes here is very different. Some of them are faster, some are slower, some of them are more available, and some are less available. And the most interesting thing happens when interactions between this data heterogeneity and device heterogeneity. Okay? So in particular, if we had a certain type of data that appeared mostly in devices or less available, we don't want to starve those out. So we want to kind of ensure good coverage, and we're really training on as much data as we can, despite both data and device heterogeneity. And there's also issues of security, right? I mean, if I like hack my phone to participate in this process in a bad way, I mean, am I going to like, can I ruin the training, or worse than ruin, like, plant all kinds of things that I can in the training. And I think one of the, many of these are very, questions with, you see very strong ties to different areas that are decided theoretically. But one particular way, which I think it's important, and came up repeatedly in kind of preparatory workshops we had, that one role of academia here is really to define different threat models. So right now, we have companies that are, running these things and saying, okay, things are safe, things are secure. I mean, they obviously have a strong vested interest in saying that things are safe, secure, private, and what so. And I think it's one of the important questions here is to kind of try to understand in what do we want to require, what kind of security guarantees we want to require. So this is, the original federated learning was this cross-device federated learning on these edge devices, but now federated learning is used to and thought about much more broadly. So we talk also about cross-silo federated learning. So this is kind of the same thing, but now it just replaced my phones with hospitals. So now you can think of a situation where there's data that's different data that's available in different like entities, like the think of it as different hospital, different patient data, and this data cannot be freely shared between hospitals, both because of true privacy guarantees or because of various regulatory constraints. And we still want to sort of train a model based on the data that's in all of that's siloed out in these different entities. Okay? And the issues here are more than just privacy. It's also like really data control, like what happens to the data. So many of the same issues come up. And here, this is an issue that comes up also for cross-device federated learning, but even more so here is issues of incentives and data valuations. Like, why should I participate in this process? Why should I make my data available? Okay? And if I make my data available, I mean, should I make like all of it available? Should I, am I getting anything for this? Okay, and I think this is an issue that really comes up also with your own device. Like many of you, get asked like, do you agree to use your data for improving the model? Okay, and the rational answer to that is of course no. Like, why do I agree? I have no incentive to agree. Okay, so can we create incentives to actually use this data? And part of that is a kind of evaluating the data and its cost. And this goes out maybe from to a more general thing, and no, the program is not just federated learning, but collaborative and federated learning. So really take a much broader view of collaborative learning, which is really, I mean, what's happening now, we're training models based on lots of different data sources, lots of different, it's held by different people, owned by different people. We really want to use a bunch of data. We ideally, training presumably all the data that you have on your laptops, all the emails you ever wrote, all the edits you ever add to any documents, all the pictures we took. It is very valuable, and I think when I say valuable, I think of it not in terms of just commercially valuable for a company, but societally valuable in order to create great models. But of course, there's a lot of challenges in doing that, for and foremost privacy, but also these challenges in terms of incentives and what are you getting out of it? Why should you share? How should you be maybe paid for that? We had a preliminary workshop discussing this. This is the issues that came up repeatedly, and so the program really shifted from one focusing more on the kind of system aspect, including privacy and reliability and ingenuity, to one that is a very strong also economic, game theoretic mechanism design component of thinking in terms of these incentives and how to design these data markets which ensure both efficiency of training and that individuals like are incentivized to do so. There's also lots of maybe more recent challenges we're constantly, I think, thinking of and have already come up in the program. Things like, how do we handle models that are too large, they can't even fit in the device? How can we train that in a distributed way and shifting to test-time compute? So as I mentioned, the program is in federated and collaborative learning. It draws together researchers from many different backgrounds, both in kind of more traditional optimization, statistics, and learning theory, and privacy, a lot of crypto to ensure secure computation, and also people coming from economics and game theory. So we're going to start in January. There are going to be 4 workshops, a boot camp, and then 3 workshops, one workshop focusing on the more kind of traditional learning and optimization approaches from heterogeneous sources, and the second workshop on trust in decentralized systems, which is going to explore topics related to privacy and security and different attacks and threat models. In the third workshop on agency and collaborative learning, which is really going to explore the more economics and incentives, and really with this very user-focused view that what is the incentives and how can we make things good for individual users. And I should say this is there's, as I mentioned, a lot of interaction with industry. I've highlighted in blue here the long-term participants from industry, and we have already also many confirmed speakers from various companies. This is very important to us because we want to really both develop, so there's lots of interesting questions and develop methodology that's actually relevant, but also try to influence what's being done in various companies. And federated learning is now, I hope I don't have to tell most of you that this is something that's being deployed now at scale in many places. Okay, so let me just finish here. Thank you.
One thing I'd point out about these workshops is pretty much all our workshops are the call for participation goes out a couple of weeks before, and we have open registration. So if you're interested in the topics, especially for the spring programs, program on federated learning, which is very relevant to what's happening in industry, check us out, register, come. You're welcome. And so, okay, for the final talk of the session, we have a special treat. So high-performance computing and large-scale numerical computation simulations has been one really exciting area for synergy between theory and practice. And we have Jim Demmel, who will give us a little bit of an historical perspective on how major developments in theory have fueled very important advances in practice, as well as some of the ongoing work in this space, both under the auspices of the current programs as well as beyond that. So that's we'll hear from Jim, and then we have a break.
Okay. So welcome, everybody. It's a pleasure to be here. And so I've been working on algorithms that avoid communication for a long time. And so it was a great, which means, communication means moving data, between different processors over a network or between DRAM and cache. So it was a pleasure in the first week of this workshop, because there are 2 workshops. There's complexity in linear algebra, and there's emergent emerging architectures. And every speaker in the emerging architectures workshop began their talk by saying, communication is the most expensive thing. So that was a good thing to hear. And so here is a very recent slide documenting this from Dave Patterson, which shows now this is not the cost measured in time, it's a cost measured in energy to do all these different operations. And there's a factor of 45,000 difference in energy cost between doing a single 8-bit add on a chip versus going off to DRAM and actually getting the data that you want to add. So people notice a factor of 45,000. And so, so it's no surprise that there's a lot of motivation these days, and I'll get to that at the end of my talk, to use the cheapest thing that you can possibly do, which is 8-bit arithmetic, to do 64-bit arithmetic and give the users the same answer they got before. But there's a question of what that means. And so there's a lot of interesting work going on there, too. So whether you're most concerned about the battery in your cell phone dying or the $1 million per megawatt per year it costs to run your data center, or how long your drone can stay aloft, or climate change, you should worry about energy, not just time. And so the goals of this long-term research project, which have many, many people, I'll have a list at the end, is to redesign algorithms to avoid moving data, to avoid communication. And if you know how computers, traditional computers are built, you have an L1 cache, an L2 cache, maybe more. You have DRAMs, a bunch of processors connected over a network. You'd like to minimize the amount of data moved over all of those. And what we'd like to do as theorists is have lower bounds. Have a lower bound proof that you have to move at least this much data in order to run your algorithm. And then, you look at the classical algorithm and say, do I hit the lower bound? And if not, well, you have to invent a new algorithm. And so this has been going on for a while. I'll just show one slide of old results before I get to the new ones, and some of which are coming out of this workshop. And there's so many different algorithms out there. A lot of the work has now gone into automation of these things. So the compiler community is beginning to incorporate some of these ideas into compilers so that you don't have to do all the math yourself. And then, of course, we have to adapt to ongoing changes in hardware, too. So I'll get there. So here's some prior work. So one thing you could ask is, well, OK, I want to run this algorithm. I'm going to do exactly the same arithmetic operations as before. I'm just going to do them in a different order so that I reuse the data as often as possible so I don't have to move it very much. And that has led to large speed-ups, up to factors of 100 for various different kinds of algorithms, like sparse times dense matrix multiply. And there's these are references if you want to look at it later. There's slide, at the end of the talk. Happy to share the slides later. So that, you can make a lot of progress doing that, but sometimes you have to change the algorithm. And in many cases, the user wants to get the mathematically identical answer, maybe a different data structure, but it's a different algorithm. And there, you can also get big speed-ups. And sometimes you end up with a different data structure, and so the whole software stack may have to change because of that. But we got lots of speed-ups from doing that, too. And sometimes, if you're only trying to tell dogs from cats or something like that, you can use a completely different algorithm with a different approximation and get all sorts of different speed-ups there, too. So just to give some example of the impact this has had on industry, since this is Industry Day, I was teaching this matrix multiply algorithm in my parallel computing course a number of years ago, and one of the students thought it was a good idea. So he formed a startup. It was called Nirvana, and it was acquired by Intel a few years later. And then, a few years after that, Thorsten Hoffler, who just won the ACM prize in computing, decided he needed to make the constant factor a little bit better. We were just a big O kind of team, and he got the constant right, and that won another Best Paper prize. So our algorithm for doing least squares, QR, that won a Best Paper prize, and we got into LAPAC shortly after that. And support vector machines, that's a 16x speedup, that won a Best Paper prize. And now, for more industrial impact, that 135x, that was adopted by the industry standard benchmark ML-Perf, which is how all of the different people race to do their ML training. So the idea was, you spend all your time doing matrix multiply, so why not just use these algorithms to, in your ML training? But if you do that and you make your matrices bigger, you don't converge as well as you did before. So the whole hyperparameter tuning had to change in order to make that work. Okay, so what is happening more recently, and especially with the Simons Institute? So let me just have 3 examples. I'll talk a little bit more about dense linear algebra, and then I'll talk about convolutional neural nets, and then I'll talk about the future of the BLAS, the basic linear algebra subroutines. So let me just tell you what the attainable lower bounds are, and then sort of translate this from math into computer architecture. So my problem is I have two n by n matrices. I want to multiply them. I have p processors, and I'd like to use whatever the latest best matrix multiply algorithm is. So we'd like results that even will work next year when someone makes Omega a little bit smaller. And so we need to know a little bit more about our hardware. We also need to know how much memory we have on each processor. And each processor comes along with some memory, and the way we're going to measure that is how many copies of the data can I afford to have. Now, I need at least n squared over p to store every matrix once. I'm leaving out a factor of 3 here. But it's often the case, as we'll see, that I can afford to have more than one copy of the data. And it turns out that's going to affect my cost. And so here is the theorem. I'm not going to go into the details, but this is how much data you have to move from one processor to another. That's the bandwidth cost. And it depends on the matrix size, how much memory I have, the number of processors, and whose best matrix multiply algorithm I have. And there's the magic formula. And to prove that requires expander graph theory, group theory, functional analysis, and all sorts of stuff that I don't have time to go into. But that gives you the proof that this algorithm hits the lower bound. And we actually have an algorithm that attains it. And it only works for when as the memory grows up to a certain limit, and then you hit a memory-independent lower bound. And the latency cost is also, just a factor of m smaller than that. That's attainable. So that's very theoretical. So what is a more practical way to interpret this? The first consequence is you get perfect strong scaling in time. If you increase the number of processors by some factor, say, double the number of processors, you run exactly twice as fast. And that's because if I increase the number of processors, I'm also increasing how much memory I have. And that means I can increase that C factor. And so that means the number of flops per processor, the bandwidth cost, and the latency cost all scale by how many more processors I have. So that's sort of a nice outcome. So that's time. But there's also energy. You get perfect strong scaling in energy. So what does that mean? So what's my cost model? Well, depending on your computer, each floating point operation will cost a certain number of joules. Just turning your memory on and keeping it on for a second, that costs a certain number of joules. Moving a word, a message, packing it together, and keeping the fans on, all that kind of extra stuff, that costs a number of joules per second. And so it turns out that if I increase the number of processors by a factor, the total energy remains constant. I can do it, if I double the number of processors, I can solve the problem twice as fast and use no more energy. And the mental model is I'm burning twice as much power for half as long if I double the number of processors. So it all kind of works. And so this led to an interesting conversation after the presentation at Simon's, because there's a bunch of people in the architecture program who are building 3D chips. And where you have not just the usual two-dimensional model of a chip, but you have multiple layers. And so the question that we began talking about, ongoing conversation, is do these algorithms map to those kinds of chips in a reasonable way? So one thing I didn't mention here, but it's going to be important, is to hit this lower bound, the topology of your interconnect network has to be at least three-dimensional. You can't just talk to your immediate nearest neighbor and hit all these lower bounds. And so these three-dimensional chips might give us an opportunity to deal with that. So what about the rest of dense linear algebra? So one nice thing that came up was that when I was talking to one of the participants who was coming up with these new theoretical algorithms, I learned he had a startup. And I knew about another startup in Silicon Valley, so I put the two CEOs together. And so there's going to be a meeting shortly to talk about whether these two startups can share the ideas. But let me just, we'll see what happens with that. So our aspiration, of course, is to apply these ideas that work for matrix multiply to the rest of dense linear algebra. And so here is a sort of some bad news. So let's suppose I want to parallelize Cholesky, which is sort of the next thing you would do after matrix multiply. And let's suppose I'm just going to do the classical n-cubed algorithm. Then there's another lower bound, which says the bandwidth cost times the latency cost can't get smaller than n squared. So I can't make them both smaller at the same time, which is what I was doing with matrix multiply. And so I can make the bandwidth go down, and so that means perfect strong scaling is impossible, alas. But I can hit the lower bound for bandwidth as I increase the memory, and that's a good thing. And I can also do it for Gaussian elimination, but I need to throw away partial pivoting. But I still need to get the right answer, so I have to do a different algorithm. It's not partial pivoting, we call it tournament pivoting. And something that's new that's happening this semester with a bunch of people here is we have a new so-called 2.5D algorithm where we can go faster with more memory for the eigenvalue problem in the singular value decomposition. So hopefully we'll get that written up and posted in a few weeks. So let's go on to machine learning and see how that looks. So what's a convolutional neural net? Here's just a picture. It's basically 7 nested loops. I have a bunch of images, and I have, red, green, and blue, or whatever, a bunch of channels, C. And I have a bunch of filters. I move each filter around, and I compute a dot product, and I get an output. And you can write that down as 7 nested loops. And so ideally, I would like to extend my lower bound theory, which works for matrix multiply, to something messy that looks like this. So it turns out it's a little bit more complicated, and we had to write a computer algebra program to actually prove the lower bound and find it was actually attainable. And the lower bound is going to be proportional to how many loop iterations there are. That's just the number, product of all the 7 loop bounds. And this is a sequential algorithm, so it depends on the cache size. So I want to minimize data movement between DRAM and cache. And the answer could be the max of any of 5 terms. The size of the output, the size of the input, size of the filter. Obviously, you have to read and write each of those once. Then it turns out you can go much faster than matrix multiply, which is interesting because the classical way people implement convolutional neural nets is they map it to a matrix multiply. And they say, well, that's the best thing you can do. Well, no, you can do much, much faster. And if you actually have very large filters, which is maybe a little unrealistic, if this were matrix multiply, it would be n divided by the square root of m. So we're asymptotically faster by a factor of the square root of m. But the filters are usually not enormous. So here's the actual practical lower bound. And you get this complicated function of the sizes of all your filters and how much you shift them around. And that also beats matrix multiply. And any one of these terms should be largest. And so that's sort of the detail. And the theorem is it's always attainable, and that required a computer-generated proof. And some people have been trying to implement this in hardware. So what's left in all this world? So ideally, we'd like to be able to handle arbitrary code that looks like nested loops, accessing arrays with arbitrary subscripts, I plus j minus 2k, whatever mess you want. And it turns out we can do that. There's an attainable lower bound using lots of group theory and functional analysis, but we have to ignore dependencies. So, if you have to do this loop bound iteration before that one, like in Gaussian elimination, we don't pay attention to that. It's sort of just for matrix multiply. And the loop bounds also have to be large enough. Then we can attain it. So that's sort of nice, but it's mostly theoretical. So why do we care about small loop bounds? Well, you can think about matrix vector multiply, and that's a special case of matrix multiply, except one of your matrices is really skinny. And we can't optimize that because you can't fit your square tile size into a single vector. And CNNs also have very small loop bounds for the filters. And so what we'd like to do is solve this problem in general. Here's a special case. If all of your subscripts are very simple, like I, j, k, and you're iterating over a parallelepiped, a square or a cube, then there exists a new lower bound, which is attainable and tight. And it sort of gives you the obvious answer for matrix multiply, and matrix vector multiply, and everything in between. So a square matrix times a skinny matrix. So then there's dealing with dependencies when you can't reorder everything in an arbitrary way. And we've obviously done that in special cases like Gaussian elimination and all pairs shortest path, but there's lots of open problems there. And for sparse matrices, I haven't mentioned that, but it's going to depend on the sparsity structure. And so there's lots of, we have some results, but there's still lots more to do. And then, real hardware, which is what we're talking about in the other program, there's a lot more realistic performance models than just counting flops and counting the number of words moved. And so real processors are going to be using variable precision. I'll get to that. Short, how much arithmetic can you do that's short versus long? And then there's heterogeneous processors, accelerators, and network topologies. And we just heard in the last talk, the cost of writing data and reading data is very different. And so what we need to do is have bounds and algorithms that separately minimize reads and writes. And we can do that in some examples, but there's still lots of open problems. So then there's sketching, where we need to multiply our input matrix times a random matrix, because we're doing randomized linear algebra. And we can actually beat matrix multiply. You don't have to, you can, and the idea is that if it's cheap enough to generate a random number on the fly, you just generate them on the fly instead of reading them from memory. And you can do asymptotically faster. And as I said, the compiler community is getting into this business and saying, oh, we need to automate all this. And so there's a link. So let me end with an example which has a very nice link to the Simons Institute here. So I want to talk about the future of the BLAS. And as I mentioned, a lot of vendors are building low precision matrix multiply accelerators, 8-bit accelerators, because that's what machine learning is all about. And that is getting much, much faster, but not necessarily FP64. In fact, in the last NVIDIA release, FP64, 64-bit floating point, got slower than the previous release. So Moore's law has turned around. And so what they're all very motivated to do is provide fast matrix multiply by emulating the 64-bit arithmetic using lots of lower precision. And so the question is, what can they promise, or what should they promise to the users who are expecting to have high precision arithmetic? And so and I'm on the BLAS committee, so this is our problem. And so what we have to do is come up with a way of grading the BLAS. And I'm not going to write down all the formulas, but we've decided that you can get either an A, a B, or a C grade, depending on how accurate your matrix multiply is. And an A means you get the classic error bound from a numerical linear algebra class, running the n-cubed algorithm. A C is what you get from a Strassen-like algorithm, which is a weaker bound, but it's still useful for lots of things. And B is somewhere in between, and it just has this sort of row and column scaling invariance. And so NVIDIA has decided to adopt this scheme and deliver a version of the BLAS that promises you an A. And they're willing to do an extra n-cubed work to decide if it's OK to use their fast matrix 8-bit arithmetic. So they do an extra, it's 10% overhead. They sort of just do a matrix multiply-like operation on the exponents of the data to see if the exponent range is narrow enough. And when they adopted this, I got a nice thank you note from Jensen Wang for this, because this is what they decided to do. And so what is the approach? They're going to revert, so what is our approach to try to do this grading? What we need to do is reverse engineer the algorithm. We have to come up with some test matrices that sort of extract, are you doing Strassen? Are you doing 8-bit arithmetic? Are you doing some other kind of floating point inside? And by doing clever choices of test matrices. And the challenge to do this is that our tests are going to be completely public, because that's the way the BLAS are, but the implementations we're testing are proprietary. We can't see them. So the question is, how do we come up with ungameable tests for all these vendors? And so we thought we had an ungameable test for a Strassen-like algorithm. And the idea was very simple. You pick a bunch of random rows of A, make them randomly sparse, pick some columns of B, make them complementarily sparse, so all the dot products are sums of zeros, and only if you actually did a dot product would you get a 0. Otherwise, you get the round off that came out of Strassen. And as I was presenting this here in this auditorium a few weeks ago, someone in the audience immediately came up with a way to game that. And so we had to go back to the drawing board and figure out a new way to do it. And I'm embarrassed to say I don't remember who suggested that. I want to give them credit. So if you or you remember who made that suggestion, please let me know. And so we're still working on that counter strategy. So this is a great outcome from Simons. And so this is joint work with lots of people over many years. And so here's just a list. I hope I haven't left anybody out. And to summarize, it's time to redesign all of linear algebra, machine learning, and algorithms and software and compilers. And what it all has in common is don't communicate. That's it. Thank you. And there's lots of references if you want to find more details.
It's time to ask Jim some questions.
So the suggester of the new game isn't here, I guess.
All right. If there are no questions, yeah, you can certainly catch the speakers during the break. We have a break now till, I believe, 11 a.m., and we reconvene for talks from our industry partners. Thank you. Thanks to all the speakers.